This ignition delay time is the time elapsed between the start of fuel injection to start of combustion, right? That time duration is referred to refers to the time that is required to form an ignitable fuel air mixture. To form an ignitable fuel air mixture, some amount of time is spent in the engine after you inject the fuel into the cylinder. That delay time is referred to as physical delay time. There are various processes that are happening in a sequential manner after the fuel is injected in the engine cylinder. These are the processes that happen during the after the injection of fuel into the engine cylinder. These are the various processes that happen one after other. That's why I use a word in a sequential manner. So these processes happen one after other after you inject or spray the fuel into engine cylinder. So the time required for all these processes put together is referred to as physical delay time, which is a time required to form a ignitable fuel air mixture. Then there is another delay time referred to as chemical delay time, which is a time required to form radicals from a stable molecular structure of the fuel. From a stable molecular structure of the fuel, radicals are formed, and the time required for forming that radical is referred to as chemical delay. Okay, so as we have discussed in the previous class about overview of combustion events. So here we know that the fuel as such is having a stable molecular structure. Okay, so what we do here to initiate combustion is we provide activation energy. To initiate the combustion event, the way the activation energy is provided is different for SI engine and CI engine. In a spark ignited engine, how do we provide activation energy? We discussed this in the previous class.
So through spark plug.
Through spark discharge. Through spark discharge, you are actually providing activation energy to initiate the combustion. So when you discharge high voltage electric spark, you are actually providing sufficient activation energy or thermal energy to form radicals from this stable molecular structure. So radicals are formed because of this. The combustion event will get initiated. So there is a radical formation which initiate the combustion process. So once the combustion process gets started, it will go on its own. It is a self-sustaining process. No need to do anything. You have to just initiate the process. Once the process is initiated, it will go on its own as long as sufficient radicals are available. These radicals are active chemical species. They are in an unstable state. They will try to reach a stable state by reacting with other molecule. That is how the combustion event is carried forward. It's a kind of chain reaction. Okay, so we have to initiate radical formation. Once they are formed, the process will go on its own as long as sufficient radicals are available. That's why it is called self-sustaining process. Combustion is a self-sustaining process. Okay, so in a SI engine, we do initiate combustion event by discharging high voltage electric spark. In a CI engine, what do we do? It's through compression process.
Compression.
So you are compressing air to a high pressure, high temperature, right? Because you are maintaining a high compression ratio in the engine cylinder. So you compress it to a high pressure and high temperature, and then you spray the fuel into the high pressure, high temperature air. This air is providing activation energy to form radical. Okay, so there is a time elapsed to form radical from the stable molecular structure of the fuel, and that time is what is referred to as chemical delay. So there is a physical delay, there is a chemical delay. During physical delay, there are sequence of processes happening, and what you see on the right hand side in the red bubble is the various fuel properties that are affecting each of these processes. Each of these processes are affected by these fuel properties. Okay. So this is what is the role of fuel. The fuel will play a significant role in influencing each of these processes. Okay, this is what we are looking at here. Okay, so this is a diesel engine combustion, first stage of combustion. These are the processes and these are the fuel characteristics that affect each of these processes. So we use an injector, as you are familiar with this. So we install this injector in the cylinder head and then spray the fuel. You will have n number of orifices around the circumference of the injector tip. Okay. And so here, this particular injector has around 8 spray profile. You will have n number of spray profile and they are evenly placed, as you could see here. They are evenly placed around the circumference of the.
Yes, sir.
Yeah.
Hi, sir.
Sir, just a quick query, sir. What is the orifice diameter generally?
It will be in micron. It will be in micron, few microns. Micron is 10⁻⁶ meter.
Oh, okay, sir. Okay, sir. Thank you, sir.
So you are spraying fuel into the engine cylinder. What do you have? This is a bottom view. Okay, so you are spraying fuel into the engine cylinder. What you have in the cylinder is air at high pressure and high temperature. Okay. Once you inject the fuel into the engine cylinder, these are the processes that are happening, which involve physical delay to form an ignitable fuel air mixture. And then there is a chemical delay, that is the time required to form radical. So you will have n number of fuel sprays, okay, fine sprays. And the objective here in having n number of fuel spray is we want to utilize air as uniformly as possible. You have to improve the air utilization. So we use the term air utilization. You have a limited space or volume inside the engine cylinder wherein you are spraying the fuel. And what you have in the cylinder, you have air. So the spray has to utilize the air as uniformly as possible, because the spray has to undergo various processes, and these processes, so you know that the combustion is a gas-phase phenomena. What you are introducing is initially a liquid phase fuel. This liquid phase fuel has to get into gas phase fuel. Okay, and then this fuel in the gas phase has to mix with air in the finite proportion. Fuel and air cannot ignite at all possible proportion. It can ignite only at a finite proportion, which is called ignitable range, which is a property of the fuel again. Okay, so fuel and air can burn only if it is mixed in a finite proportion. This is what I mean by ignitable range. Okay, so you are introducing liquid phase fuel. It should get converted to gas phase. It has to mix with air in a finite proportion called ignitable range. Then only ignition can happen. The time required for all this is physical delay. Once it forms an ignitable range, it will form radical. Radical formation will be initiated. That is what is the chemical delay time, right? And then fuel start burning. You could see that the spray burns initially from the outer periphery. It will gradually spread, and then from there it spreads across the engine cylinder. That is how the injected fuel get burned. Okay, by utilizing air in the engine cylinder. So now here. So you have a delay time, which is the time difference between start of fuel injection to start of combustion. This is what is ignition delay time. Okay, as indicated here is the time elapsed between the start of fuel injection to start of combustion. And this includes two elements. One is physical delay time, which is the time required to form ignitable time, which is the time required to form radicals from a stable molecular structure. Okay, so in the physical delay, as I have shown in the slide, you have several processes that are happening in a sequential manner. So you have a spray breakup, you have atomization, you have air entrainment, then vaporization, mixing. So here I have shown those with a simple schematic. The photograph of that I have shown earlier. So you have a fuel injector spraying fuel into the engine cylinder. The pressure at which the fuel is sprayed is dependent on the injection system that you use. Off-road diesel engines generally have a mechanical injection system wherein the injection pressure is typically 300 bar. On-road automotive engines generally use electronic fuel injection system, wherein the pressure can vary anywhere between 300 to 3000 bar. common rail direct injection systems are used, and which can be used to achieve pressure values up to 3000 bar. So the takeaway for you is you are spraying fuel, you are injecting fuel into air at a very high pressure and very high pressure, which will result in very high velocity. Okay, so spray will move inside the engine cylinder at a higher velocity because of this higher pressure. What do you have inside the cylinder? Air exists in the cylinder at this typical condition, 30 bar and 800 Kelvin. These numbers are typical numbers. It is going to vary. When do you inject fuel in an engine operating cycle? When do you inject fuel in the engine operating cycle?
At the end of suction stroke.
At the end of
Few degrees before TDC, sir.
few degrees before TDC, during which stroke?
Compression
Compression
stroke.
stroke.
Compression stroke.
So we are basically most of the engines, as I have shown in the previous class, most of the engines are 4-stroke cycle because they are most versatile. 2-stroke engines are very limited application. Okay, for our discussion, I have considered 4-stroke. So the fuel is sprayed into engine cylinder during compression stroke, near the end of compression stroke, few degrees. Generally, it is around 10 to 20 degrees before the piston reaches top dead center, which is a reference point. Okay, which is a reference point always when we do combustion analysis. I will talk more about this reference point as we move on. We are spraying fuel into engine cylinder before the piston reaches TDC, few degrees before TDC, typically around 10 to 20 degrees before the piston reaches TDC. Because of that, you already have compressed air to a high pressure and high temperature. Typical values are shown here, 30 bar and 800 Kelvin. Okay, and this number is going to be dependent on what? The pressure and temperature of air at the time of fuel injection is dependent on what?
Initial temperature of this.
Sorry?
Compression ratio, sir. Compression ratio.
Compression ratio, exactly.
Compression ratios.
So it depends on the compression ratio of the engine. And you know, compression ratio varies anywhere between 17 to 22 in a diesel engine. This is a common range. Okay. So it's not one value, it's in a range. It's going to be optimized. It's one of the important design parameters which needs to be optimized based on the intended application of the diesel engine. So you have
Sir, sorry, also it depends on the turbocharging or supercharging, sir, if it is applied for the
yeah. So this is for naturally aspirated. For a turbocharged engine, it also depends on the initial intake pressure, which is slightly above. You have a boost pressure, right? Few bar,
Yes,
right? Ambient pressure
sir.
is 1 bar, and turbocharger pressure may be anywhere between 1.1 to 2.2 bar, just above the ambient pressure. And that will also decide this pressure. Air pressure reached at the end of compression will be dependent on initial air pressure, intake pressure.
Okay.
So these are the parameters that affect condition, air condition at the time of fuel injection. These are some chemical numbers I have given. So when you spray fuel at a high pressure, the fuel will have to encounter the air resistance because air is at high pressure and high temperature. So you have a dense air inside the engine cylinder and you are spraying fuel into the air, right? So once you spray fuel into the air, which is at this condition, the fuel will form a finite profile, which is shown here. It's a typical spray profile. And when you talk about spray profile, there are two important macroscopic characteristics. One is called spray penetration length, which is a maximum distance traveled by the spray, fuel spray. Other one is called spray cone angle, which is an included angle between the outer boundaries of the spray, which is what is a spray cone angle. These two are called macroscopic spray characteristic. You have penetration length and you have a cone angle. So fuel is penetrating because of its higher pressure. It's penetrating into air. Air is offering resistance for the free movement of air because air is for the free movement of fuel because air is also at a higher pressure and higher temperature. So you have a profile. Spray profile that is formed inside the cylinder, which is what we have seen in this photograph also. So you have a finite profile which is formed, which is a spray profile. You have n number of spray profile depending on the number of orifices that are located in the injector. As I said, these orifices are equally spaced in the circumferential direction of the injector tip. So you have n number of spray profiles emerging out, and they are penetrating through the air. Air is offering resistance for the free movement of the spray. So you have spray penetrating into air, forming a profile with a length and angle. Okay, spray penetration length and angle. So once the spray start moving because of its higher pressure, you are injecting at very high pressure compared to air pressure. So the spray is able to move against the air resistance. So once you inject the fuel, the outer periphery of the spray will be like a thin film. It will be like a thin film of fuel. Because of air resistance, because of the shear force offered by the air, the outer periphery of the spray will start to break. This is what I mean by breakup event, spray breakup event. So the film will break and start to form drops, as I have indicated here. So small drops will start to form, and this process is called atomization, formation of drops. So we want as small or fine drops as possible. Why do we want a fine drop? So what I mean to say here is we want to form drops with a very small size, not a larger size. What could be the possible reason?
Time of combustion.
Time of combustion?
Sir, homogeneity of the mixture, sir.
For proper mixing, sir.
For proper mixing.
Yes, sir.
Okay. Before
Homogeneity of
mixing,
mixture.
something else has to happen, right? So this is liquid phase fuel. Before mixing, something has to happen.
Proper atomization.
Atomization, sir.
Phase change.
Break of molecules, sir.
Molecule has to break up. No, this is liquid phase. Combustion is gas phase. So what should happen?
Latent of phase change, sir. From liquid to
Phase change.
what I mean to say is
Phase change.
phase change.
So phase change,
Atomization and vaporization.
Enthalpy.
yes. For phase change, what do you want? Latent heat of vaporization. So there is a finite quantity of heat you need for the phase change. Where from the fuel takes that heat?
From the combustion space, sir.
From the combustion space, what exists in the combustion space?
Air, sir.
Air,
compressed
air, compressed air. So the fuel, liquid phase fuel, has to absorb this latent heat from air. Okay. So what I said here is I want the drop to be as fine as possible or as small as possible. What is the advantage in forming a smaller drop compared to larger drop from the perspective of latent heat, absorption of latent heat?
lesser amount of heat required for
No, this is a finite. Latent heat is
Heat
finite,
transfer, heat absorption, heat transfer will be faster, sir.
faster. When you form a smaller drop, so you compare two cases, a larger drop and a smaller drop. What is the difference between these two cases?
volume.
Area increases, sir.
Surface area, sir.
Volume is high.
Density.
Surface area to volume. Right? It is going to be different. Surface area to volume is going to be different. So if you form a small drop, surface area is going to be much higher, right? With a larger drop, surface area is going to be less. So this larger drop will take more time for vaporization, right? As compared to the smaller drop, because the area exposed to surrounding air is more. Did you get what I'm saying?
Yes, sir.
Yes, sir.
Yes, sir.
So you are breaking a film at the outer periphery, forming finer drop. I want a very small drop, and this process is called atomization. How fine a drop can form is what is referred to as atomization. Once the drops start to form on the outer periphery, you have space between the drops. The space between the drops will be filled in by air. This is what I mean by air entrainment. So until otherwise you have a space, air cannot move in, right? If you have a film, continuous film, air cannot enter. Now when the drops start to form, there is a space. In that space, air will go and fill in. This is what I mean by air entrainment, because liquid phase fuel has to get latent heat from air only. So you have to expose the surface area of the fuel drop to the surrounding air so that the fuel will get into the next event, which is vaporization. We want this vaporization to be as quick as possible. Please note, all these processes should happen with a very small time scale. It should happen so quick. So what is the typical time scale?
So microsecond.
Milliseconds, sir.
Micro, milli, or nanosecond. It is dependent on the engine running speed. So based on the engine running speed, one cycle time, engine cycle time is the time required to complete one operating cycle. That is going to be very small based on the engine running speed if it is higher. So based on the changes in the engine operating speed, the cycle time is different. Based on the cycle time, these processes, the time taken by these processes should be accordingly lower, because these processes are happening during a fraction of an engine operating cycle. These processes are happening during this is the first stage of combustion event, which is the fraction of engine operating cycle time. So all this should happen with a very small time scale, typically nanosecond, milli or micro. Milli is a coarser time scale. Nano is what will generally happen. That is 10 power minus 9 second. You can imagine. So that is the time scale we are talking here. So there is an air entrainment followed by vaporization, because the fuel absorb heat from latent heat from air, get into gas phase. Okay. Then once it get into gas phase, the next process will start, fuel air mixing. Right, the fuel and air has to mix in a finite proportion, which is defined by a term called equivalence ratio. I will talk more about this equivalence ratio as we move on. This is one of the important parameter when we do analyze the combustion event. Okay, so the fuel get into gas phase, mix with air in a finite proportion. It should mix in an ignitable proportion defined by equivalence ratio. Then the total time involved in all these processes put together is a physical delay time. Once I get into this, whether the ignition will happen immediately, no. I have an ignitable mixture. The ignition again takes some time, and the time is a chemical delay time, wherein I am forming during this chemical delay time, I am forming this radical, okay, from a stable molecular structure. By providing activation energy to ignitable mixture, you are initiating radical formation process. And that is how the ignition will start to happen. Okay, so that time involved is called chemical delay time. And this is governed by chemical kinetic scheme. As we move on in the second chapter, I will talk about this chemical kinetic scheme. And this is dependent on the molecular composition of the fuel. So what will happen during this chemical delay time? You have a chain initiation reaction, chain propagation, chain branching, and chain termination. All this put together is referred to as a chemical kinetic scheme. Any fuel will have a chemical kinetic scheme, which include these 4 basic reactions, chemical reactions, and basically these reactions involve radical formation and radical consumption. As I said, the combustion event will get started with radical formation, and it will continue on its own as long as sufficient radicals are available. Once all the radicals are consumed, the combustion event will get terminated. We do research on optical engine apart from metal engine. Anybody has done any research on optical engine? Not yet.
Sir,
Yeah.
during like TVS company, I have seen one of the 2-stroke engine with optical running, like one transparent head they have prepared, and then the
So in an optical engine, you can take images of the combustion event. You can track the combustion event. It provides a better analysis of combustion event and optical engine, because you can take images, you can record and analyze the images to see how the combustion is happening. So one of the important information you derive through optical engine analysis is we will track this OH radical. OH radical formation is an indication of start of combustion. Start of combustion or start of ignition is tracked by checking when this OH radical is forming. Formation of OH radical is an indication that the ignition is going to get started. Okay, so when we do research on optical engine, we will keep a check on when this OH radical is formed in the engine cylinder, because that is an indication of start of combustion. Okay, so we do track this, and this is happening during the chemical delay time. Now, when you look at this physical delay time, the influence of fuel properties, and this is highlighted here. So you inject the fuel. I use the word volumetric fuel injection because in a diesel engine, in SI engine also, we meter fuel on a volume basis. So I'm using the word metering. I think you are familiar with this term metering, right?
Yes, sir.
So metering is allowing a finite volume of fuel into engine cylinder for each cycle, each engine operating cycle. This is what is metering. This metering is done on volume basis, not on mass basis. You are not metering a finite mass, rather you are metering finite volume. So you store fuel in the engine on volume basis. You meter fuel with your injection system on volume basis. We never do it on mass basis. So there is a volumetric fuel injection into engine cylinder. Because of this, density will play a role here. What is the role played by density because of volumetric fuel injection? What is going to be different based on density?
The power of the
Mass.
mass of the
Mass
engine.
only.
Exactly. Mass is going to vary. Yes, mass is going to vary based on density changes because density is fundamentally mass per unit volume. So what you meter in your injection system volume. So you are keeping this as constant. Okay, you allow a finite volume, a constant volume of fuel into the engine cylinder per each cycle. Now, since this volume is constant based on density variation, suppose if density of the fuel is high, what will happen to mass?
Will increase,
Mass will
sir.
increase.
Mass will increase. Suppose if density is less, what will happen to mass? Mass will reduce. So the mass of the fuel that goes into engine cylinder for each cycle is going to be dependent on density of the fuel. High density fuel generally allow more mass. This is where diesel fuel plays a role, upper hand here compared to gasoline or petrol. Gasoline or petrol has a typical density value of around 740 kg by meter cube, whereas diesel is having 840 kg by meter cube density. So diesel is a high density fuel. So for the same volume of fuel that is metered, diesel provides more mass compared to gasoline. This is one of the reason. There are other reasons. As we move on, you will get to know more about it. This is one of the reasons why diesel engines are more economical. Fuel economy is higher compared to gasoline. Density of diesel is higher. So for the same volume metered, the mass that goes into cylinder is more. So when more mass goes, you know, energy release is a function of mass. Combustion energy release is product of mass and heating value or calorific value. I will talk more about it as we move on. The product of mass and mass flow rate and calorific value is what is the energy release. This will decide the energy release, right? This is constant. It's a property of the fuel. What is the variable here? M dot F is variable. So based on density variation, the mass that goes into engine cylinder is going to be different. Accordingly, the energy release is going to be different for a constant heating value. Okay. So due to volumetric metering in our injection system, density plays a role here. And we prefer to have a high density fuel because it results in higher energy release compared to a low density fuel. Then comes the other process which I have just now discussed. You have a breakup, you have atomization, you have an entrainment, air entrainment. This process happen one after other in a sequential manner. And these properties, viscosity, surface tension, and density affect these processes. How it affects, you know, these are fundamental fuel properties. Viscosity is a measure of resistance for the free flow of fuel. You know how a water flows and how an oil flow. Oil is highly viscous compared to water. Okay, and surface tension decides the breakup event. Okay, when the fuel is having a high surface tension, it will resist the breakup. When the fuel is highly viscous, it will form a larger drop size. High density and high viscosity fuel will form a larger drop size. So atomization will be poor if you have a high density and high viscous fuel. Okay, because they are going to form a larger drop size, which will take more time for vaporization. As I already told you, these processes should happen in a nanosecond time scale, very, very small time scale, right? So we should not delay any of these processes that is going to affect the overall combustion event. And these properties are affecting that. Viscosity, surface tension, and density. You need to keep a check on this property because they will create adverse spray characteristic in terms of a larger drop size. That is one effect. The other effect with the high density fuel is when the fuel is having high density, the penetration length will be more. The penetration length, the spray penetration length is dependent on the momentum of the spray. What is momentum? Spray momentum?
Mass into velocity, sir.
Mass into velocity.
Mass of the fuel multiplied by velocity of the
velocity.
injection.
Velocity is based on what?
Pressure
What will
difference.
decide the velocity?
Pressure difference across the injector.
Pressure difference across the injector. So it is primarily decided by injection pressure, right?
Right, sir.
So you have a fixed injection pressure. It means you have a fixed velocity. So this is maintained and this is maintained because of that. What will vary due to difference in density is the mass, as I have already said. when you have a high density fuel, you will have a high mass, okay, that goes into cylinder. So the spray momentum will be higher for the high density fuel compared to low density fuel. When spray momentum is more, you will have sometime it may cause something called the spray wall wetting. So the spray may go and hit the wall. You know, wall is a cooler region in the engine combustion chamber because you are providing cooling water circulation around the wall region through a passage, coolant passage, you are circulating coolant. Okay, so when the momentum is more and the spray penetrate all the way, sometimes it may go and hit the wall. And once it hit the wall, it will form a film, and this film will take more time for vaporization. It will result in pollutant emission, which we are going to discuss in the second module. Okay, so what I mean to convey here is, depending on density variation, the momentum of the spray is going to vary for a fixed injection pressure, right? That may cause variation in the spray characteristic. That may cause variation in the pollutant levels that are formed in the engine cylinder. So this is a role played by the fuel and its property in influencing these processes, atomization and breakup event. Okay. And then you have vaporization. This vaporization happens by absorbing latent heat from air by the fuel, and you have a bunch of properties indicated here. Volatility is a boiling range of fuel, then latent heat, just now we discussed, thermal conductivity, vapor pressure, specific heat. All these are referred to as thermophysical properties. This thermophysical property will decide the rate of vaporization. The rate at which the vaporization happens is governed by this thermophysical property. So we need to have a better thermophysical property so that the vaporization rate is increased. Okay, so this is what is being influenced by the fuel through its thermophysical properties. It affects the rate of vaporization. Then mixing, fuel air mixing, it is governed by diffusivity. Through Fick's law, you know that the diffusivity or diffusion coefficient, right, it affects the mixing event, fuel air mixing event. It actually governs how the fuel spreads in the air. So fuel has to diffuse, spread in the air so that the mixing happens, and then the combustion event will start to happen. Okay, so fuel and air has to mix in finite proportion. Fuel molecule should diffuse into air molecule so that you prepare an ignitable mixture. And this time elapsed is called delay time, physical delay time. Once you have this, then you have a chemical delay, which is primarily governed by molecular composition of the fuel, and which in turn affect how quickly the radicals are formed from a stable molecular structure. So until this point of time, we are forming a ignitable mixture. After this, we are forming radicals from the stable molecular structure. So this is the role played by the fuel in influencing the combustion event in a typical diesel engine.
Professor, sir, one question I have. Can I ask, please?
Yeah, yes.
Professor, sir, this between the chemical delay and the physical delay, which is more prominent in terms of time domain?
Yeah, so generally you will be surprised to know that most of the time chemical delay time will be more compared to physical delay time. All this process generally will take place quickly in a typical diesel engine because of favorable conditions, in cylinder conditions. The fuel will get into ignitable range so quickly, meaning that the delay time, physical delay time is generally less compared to chemical delay time.
Sir, I'm really surprised. I was thinking the reverse way.
Yeah, because there are so many processes, you may think that each of this will take more time and overall delay time will be more, but generally, this is general trend. Generally, this is less compared to this. The fuel will, liquid phase fuel will get into ignitable range quickly, so quickly, but after that, there is some time elapsed due to chemical delay, due to radical formation process. Okay.
Thank you, sir.
So I'm summarizing here in terms of major influencing role of fuel on CI and SI engine combustion. What we have discussed just now is a CI engine combustion, which include delay time as a first stage of combustion. So this fuel, through its characteristic, it affects the start of combustion. Right, the combustion event, how long the combustion event will get started after the fuel is injected, it is influenced by the fuel characteristic. And this is primarily affected by the ignition quality of the fuel. After the injection of fuel, how quickly the fuel will ignite is based on its ignition characteristic, ignition quality of the fuel, and that is measured by using parameter CTN number, right? So ignition quality is a qualitative term. To quantify it, we have a measurable property called CTN number. So we prefer to have fuel with some minimum CTN number. This is what fuel specifications indicate. As we move on, I will show you some of the typical specifications of the fuel. One of the important requirement is this minimum CTN number, right? So fuel should have a better ignition quality so as to quickly start the combustion event. Otherwise, if the fuel doesn't have the required ignition quality, the start of combustion will take a longer time. What will happen after the introduction of fuel? What will happen if the fuel takes more time to start the combustion event?
There will be excess fuel in the fuel mixture, which has been unburned fuel.
Unburned hydrocarbons.
After burning will happen, sir.
After burning, unburned, there is more severe problem. After burning, unburned will be part of that, but there is a other bigger problem.
Knocking, sir.
Excessive temperature rise.
Knocking.
Temperature rise.
Knocking, sir. Knocking.
Misfire.
Misfire, yes. Too long, the cycle may misfire, as you rightly said. That is one problem. But more severe problem is knocking can happen because once you inject the fuel, it has to start ignition as quickly as possible. If the ignition event is delayed, if the delay time is so long, what will happen? You are injecting more and more fuel during the delay time. Once the ignition happens, this larger volume of fuel injected and accumulated in the engine cylinder will start to combust and start to release a large fraction of thermal energy, and that may eventually damage the engine. So you have a very high pressurized rate in the engine because you have a larger accumulation of fuel in the engine, and that start to form, that start to burn instantaneously. Instantaneous burning of large volume of fuel will result in large thermal energy release that may damage the engine. So you may have abnormal combustion and damage to the engine if the start of combustion is delayed too much. That's why we should have fuel with a better ignition quality. This is one of the fundamental fuel quality requirement for CI engine application. You need fuel with a better ignition quality defined by CTN number. So you need a minimum CTN number. Otherwise, you should not use that fuel in an engine, which may eventually lead to engine damage. So this is a major role of fuel. Through its ignition quality variations, it affects the start of the combustion event. In a spark ignited engine, the requirements are just opposite. So you need fuel with a better antenna quality. Otherwise, you will get into abnormal combustion or knocking combustion. So the way the knocking happens in a SI engine is different. I will talk more about it in the combustion chapter, but here we are looking at from a fuel perspective. Okay, so the way the knock happens in a SI engine is different from how it happens in a CI engine. In a SI engine, it's a flame propagation based combustion event. Once you discharge electric spark, a flame will be formed around the spark plug region. Then this flame has to propagate across the combustion chamber. Okay, and when the flame propagate across the combustion chamber, it is igniting the unbound mixture. At any point of time, the mixture should not get ignited by itself. It's called self-ignition. In a CI engine, it's the combustion event itself is a self-ignition based event, but in an SI engine, it's totally different. It's not self-ignition. The ignition should happen only with the aid of flame. What will happen when you have a poor antenna quality fuel? The fuel will start to self-ignite even before the flame reaches the fuel air mixture. This self-ignition will result in very high thermal energy release in a small fraction of time that eventually cause engine damage. Very high pressurized rate. Same thing, whatever I have said just now, but the way it happens is different. It's because of self-ignition. The flame, if it happens by itself, when the fuel air mixture self-ignite, then you have a knocking or abnormal combustion in a spark ignited engine. So one of the fundamental fuel quality requirement here is the fuel should resist ignition. That is defined by antenna quality, which is measured by a property called octane number. So we want fuel with a minimum octane number for use in SI engine. Otherwise, it will lead to knocking combustion, which will damage the engine. Okay, this is one of the important fuel quality requirement for SI engine application. Fuel should have antenna quality, better antenna quality, meaning it should resist self-ignition. It should not ignite by itself. It should get ignited only with flame. So you have one end, you have CTN number, minimum requirement in a CI engine. On the other hand, you have octane number, minimum value requirement for SI engine. And these two numbers, these two characteristics are just opposite. CN is inversely proportional to octane number. That's why a good fuel for CI engine cannot be a good fuel for SI engine. Okay, the requirements are just opposite. The fuel requirements, quality requirements are just opposite for this two IC engine variants. So these are the major influencing role of fuel in a CI engine combustion and SI engine combustion. As we move on, we are going to discuss more about the combustion even, but here we are looking at only from the perspective of the fuel characteristic. I will get started with the next topic. I will continue in detail in the next class. So here, so far we understood the role played by fuel in the combustion event for SI and CI engine. Now we are going to look at what criteria we are going to use to select a fuel for automotive applications. So before that, there is a larger picture. Fuel is a form of energy. So when we look at the energy demand for various sectors, transport sector is the second largest consumer of energy. What is the sector that consumes energy? First largest consumer of energy, which sector is that? Transport comes in second.
So power generation.
Exactly, power sector. So power sector is the largest consumer of the energy that is available in the world. So you know you have a limited energy resource and this is being shared across the sector. So the first major sector is the power sector. Most of the energy that is available in the world is being consumed by the power sector. The second largest consumer is transport. The current consumption rate is around 20% of total energy. That is what is being consumed by the transport sector. 20% of total energy available in the world is consumed by transport sector, and this is projected to get increased to 40% in 2040. So we are in 20s. In another 20 years, it's going to get double. So it means energy demand for the transport sector is going to increase significantly in the upcoming year. Because this is understandable because of the for economic progress, you need energy and you need the transport system, right? It plays a significant role in the economic progress of any country. So in the future, it's going to get increased because the developing nations are going to consume more energy. For developed nations, almost frozen, right? You have a constant consumption rate, but for developing nations like India, you have a projected demand. The projected demand is increasing primarily because of the role played by the developing nations like India, because their energy requirement is going to get double in the future. So transport is a primary, power is a primary sector and transport is a secondary sector in terms of consumption of available energy in the world. Out of this, you will be surprised to know that almost 99% of the demand for the transport sector is met with liquid fuel. So you know fuel exists in all three states of matter. You have a solid fuel, you have a liquid fuel, you have a gaseous fuel. In the transport sector, we use liquid fuel up to 99%. Petroleum or crude oil is around 95%. Biofuel, primarily biodiesel and ethanol. Ethanol, it's mandatory. In India also, it's going to be introduced. We are going to use up to 20% ethanol. Already in US, you know, along with gasoline, 10% of ethanol usage is mandatory. If you go to any pumping station, you will have a blend of 90% gasoline, 10% ethanol. So biofuel here primarily refers to ethanol and biodiesel, which are produced from renewable sources. Their contribution is also minimal. It's only 4%. The major contribution is from crude oil, gasoline for SI engine, diesel for CI engine. It's around 95. Just two put together, it's 99%. We use liquid fuel. Only 1% share is gaseous fuel, LPG and CNG, liquefied petroleum gas and compressed natural gas. They are the primary gaseous fuel that are being used. Its share is only 1% of the total demand for the fuel demand for the transport sector. 99% is with liquid fuel. We cannot use solid fuel for transport application. IC engines are not designed to handle solid fuel. You have only two options, liquid and gaseous fuel. Out of this, the share by gaseous fuel is negligible, it's just 1%. The remaining 99% is by liquid fuel. And out of this, 95% is by crude oil, gasoline and diesel. Only 4% is biofuel. Okay. These are the reasons for why we use predominantly liquid fuel in the transport sector and not gaseous fuel. I stop here because it's time up. I will continue this in the next class. If you have any questions, I can take your questions.
Professor, just one question which is out of the syllabus at the moment is, what is your opinion about the longevity of IC engines in India?
IC engines, the EV is going to penetrate. The current plan is, I think by 2030, they are planning up to 30% penetration of EV, at least in a smaller light and medium duty segments up to passenger car. But there are certain segments which is very difficult to be replaced completely, like heavy duty segments. Okay, that is one. And maybe EV will take over in a slower phase, not at a larger phase, because some of the technology is still immature with EV, like battery recycling, thermal management. A lot of research is going on. These things are not at well established or well researched. It's an ongoing area. So the take on this is EV is going to take over ICE at a slower phase. It cannot happen immediately, because there is a large time and investment spent in building the current infrastructure for liquid fuel. You know how many refineries we have and how much investment is made. And this doesn't come in a day or two. It's over a period of time this infrastructure is built. Okay, it cannot be completely replaced. You need a totally different infrastructure for EV, right? So we cannot completely replace the current infrastructure that we have built for liquid fuel for EV. It needs huge money. And especially for developing nations, like India, it's very, very difficult. Even developed nations are they are going at a slower pace in terms of EV penetration. So my take on this is EV is going to take over ICE at a slower phase. It cannot happen quickly. For two reasons. One is technology requirement is totally different and some of them are immature. Second one, investment and time that we have made for liquid fuel is, I would say, over 100 years or so, and it cannot be replaced in few years.
Yes, and adding to that, sir.
Yeah.
Yes, and adding to that, sir, requirement of power sector will boom. Suppose like one side we will reduce, other side it will increase, because mostly we are relying on that petrochemicals only for that power sector also.
Yeah, absolutely. So if you take our country, we are producing power primarily from coal. Okay, yes. So most of the power requirement, electric power requirement, are met with coal. You know, coal is a high carbon fuel. Tailpipe emission will be zero. That's why people are recommending to do a life cycle analysis before you take a call on EV. EV is recommended if you produce power from a renewable source. But if you take our country, we produce power from coal, which is a high carbon source. High quality coal consists of around 98% carbon, whereas gasoline or diesel consists of 84% carbon. You are actually increasing carbon emission if you go to EV with coal-based electric power. This is point number one. Point number two, you have still electric power requirement for basic needs. There are almost 30–40% of the houses, they are without any basic power for the basic need. Okay, now you're talking about tapping that power for charging your vehicle, okay, which is for the comfort, I would say, compared to the basic need. So for a country like India, it's really challenging if you move towards EV with coal-based power.
Sir, why I ask this question is, today I attended the SEAT, that is an event organized by ARI.
Yeah, they organized recently this.
Right, sir. So that is happening in Pune actually. So I went there. So 95% of the exhibition that was concentrated on EV. I just interacted with an Audi guy and I asked him, what is the future plan of Audi? Are they introducing like diesel engine? Because after they stopped producing diesel engine, their sales has dropped drastically in India. So Germans are not a very good manufacturers of petrol engine. What I have heard in that, what I experienced also, their diesel engines are perfectly on spot, very nice actually.
Yeah.
So I heard a news that Audi is planning a different series of diesel engines for the Indian market and export market. But that guy was, I don't know, he was saying, no, we are focusing only on EV and EV. I told him, what about recycling and all those things? So we are saying that it is as good as IC engines. It is better than IC engines. So I think
A lot of propaganda are going on, unfortunately, but I would strongly suggest to give a careful thought on EV, especially if we need to have a holistic picture of from where you are producing electric power, because you need power for basic need, point number one. Point number two, you are producing power primarily from coal, okay, which is a high carbon source. Basically, tailpipe emission is zero in EV, but on the holistic picture, the power that you produce is from a high carbon fuel. So it's going to release more carbon based emission. Okay, so you have to go for renewable electric power production, and that is going to be expensive. That is other, for a developing nation, it should be affordable, right? So if you have designed a vehicle with a higher cost and higher maintenance in terms of tapping power with renewable energy, the unit cost is going to shoot up. This point towards again ICE, at least for the current period of time.
Thank you, sir.
Thank you.
Sir, one question, sir. You said about transparent engine. So I just want to understand, like, does the material of the engine chamber affect the combustion? If yes, any approach has been given. If yes or no, any approach has been given to decrease the chemical delay time by adding some some catalyst.
Catalyst, there are a lot of catalysts. So your question, I would separate it into two parts. First one, whether there will be any effect due to the material that you use for optical engine. No, we carefully design material in such a way that it is not influencing the combustion event, because you have to design material to withstand high temperature with the optical access. Okay, that is one. And second one, generally optical engines cannot be run like a metal engine at all possible load and speed. Generally they are run at low load and low speed because exactly the same consideration, material consideration. And second one, about your question on catalyst, there are a lot of ignition improver additive. So suppose if you have a very poor ignition quality fuel, you have to use some additive, ignition improver additive. One of the most widely used additive is EHN, ethyl hexyl nitrate, which is an ignition improver additive. It will reduce or shorten the delay time to avoid engine damage.
Thank you, sir.
Okay, if there are no questions, I will stop here. I'll meet you tomorrow at 6 o'clock.
Thank you so much, sir.
Thank you.
Thank you. Thank you, sir.
Sir,
Thank you,
just
sir.
one point.
Yeah.
Sir, I joined a little late. By the time attendance got complete.
Hemant, okay.
Sir.
Okay.
And Rahul too, sir.
Rahul, okay. So all are present except Vikas.
No, sir. Vikas is there, sir.
Sir, I'm present. Sir. Vikas is present.
So I would recommend you to join online. Thank you.
Thank you.